Hey, Calculated Math and History, and we are going to be learning about finding the area under a curve. So in this video, we're going to try and find the area of an irregular shape. So, when you try and do that, this is one of the most common lessons you would find in a pre-cal or a calculus class. So basically, these are the fundamentals of calculus. So what we're gonna do is try to find the area of this shape shown right here. But hang on, we can't exactly measure out the shape because it looks like this, and it has a curve on it. It's very difficult to find the area of a shape when it has curves on it. If we try to compare with other kinds of shapes, like squares, rectangles, and circles, it's gonna be different because these shapes have formulas that are fixed, like a equals base times height, that is a square, or pi r squared, that is a circle, or base times height divided by 2 is the area of a triangle. The problem is, what's the formula for this? Well, you can't really find one because it's really hard to calculate, and if you grab a ruler, it's really hard to even measure. What we could do to solve the problem is, even though we have a curved line right here and a shape right here, why don't we put in lines or rectangles to fill it in, and then we can calculate each of every rectangle and see what the sum of inside here is, the sum of the area. That makes our answer a little bit more accurate, but not 100% accurate. If we wanted to make our answer even more accurate, we have to add more rectangles and make them a lot more smaller. Basically, pixels in a video game. But it's still not 100% accurate because it's still curved, and you can never ever have it 100% accurate by putting in more rectangles or pixels. But, however, when we find the area of a curve in the calculus field, it will bring us to a perfect 100%. So we can use a formula that we're going to use to perfectly and accurately measure this shape right here without having to add any pixels. To a correlation and to understand this more, if you ever played Super Mario in the 1980s, Mario doesn't look like a human. He looks more like a pixel because in the 1980s, video games literally just came out. But if you look at the real world in perspective, our world is not made of pixels like Mario and Minecraft. Minecraft is made of pixels. We are not made of cubes. So, to make things more accurate and to make things more round, if you ever play Super Mario in 2020, basically, Mario looks more like a human, not a pixel. That can show us that the more pixels we add, the more accurate our answer becomes, and the more accurate the figure right here looks more rounded. If you try to ever see it transform in a way to make it more accurate, here's the last example.
1 bit, 2 bits, 4 bits, 8 bits, 16 bits, 32 bits, 64 bits,
128 bits.
But without having to add all those bits and those pixels, we can use finding the area under a curve to get it 100%. So let's get started. To find the area under a curve of an irregular shape, there is a formula we're going to follow. The formula is the area of an irregular shape is the integral of your first boundary and your second boundary. Then you have to find the function of x or whatever you're trying to calculate and then find the derivative. So, we're going to explain 3 parts of the formula. What this crowbar symbol means, because it looks like a crowbar, what the function of x represents in the equation, and what the symbols dx or the derivatives symbolize. So let's start with the integral. So when you draw an integral, it sort of looks like a crowbar. And the reason why it is useful in calculus is because it tries to limit down your workspace, or it narrows down what you're supposed to literally be working on. When we place the numbers 1 and 4, 1 on the bottom, 4 on the top, that is saying, okay, what you are trying to calculate must be in between the points 1 and 4 on the x-axis. Here's an example. By using the symbol the integral, it's saying that here is our first boundary, do not cross the line, and here is our second boundary, do not cross the line. And you must calculate the area inside here. You can't go out of it or you'll be breaking the boundaries. So the integral is basically saying, okay, this is your workspace. Mario has to stay in between those pink laser thingies. So let's look at the second part. F of x, or the function. If you were ever in algebra and you heard of the symbols f and x, that is saying it's the function of x. One that plays a role when you find the area under a curve. Not only it makes the equation more sensible, but it also describes what the line or what the slope of that thingy is. Here's an example. Not only the 1 and the 4 and the integral is trying to limit the workspace, your function is trying to work on the workspace, or trap it in. Here is x squared. Right here, this u, aka a parabola, is also limiting the workspace. It's limiting this part, which makes a curve. So when you see an equation in calculus, in this formula, it is saying what the slope or what the line is to help shape the shape in the problem. So here's the line x squared, and here's the integral 1 to 4. What is the irregular shape of the area? Or what is the area? That's why it's called the area under a curve, because you're literally finding the area under the function that makes the curve. The last part we're going to look at is the dx, or the derivative. It will make more sense to actually solve the problem and learn it as we go. Because if I explain it right now, it could be very frustrating to shout it out, and it also could be very, very confusing. So let's actually start with the problem. So we have the integral of 1 to 4 limited. We have x squared as the line, and we have dx as a derivative. what is the area of that irregular shape? The first thing we need to do is the 1 and the 4 come at the last step with the integral. What we need to worry about is the x squared, since that is the line with the function. Rather, we have to do and merge it in with the derivative. But wait, do you remember the last episodes where we did the derivatives? It explains and calculates how fast something is constantly changing. But we're not trying to calculate how fast something is constantly changing. We're trying to find the area. So instead of finding a derivative, we have to find the antiderivative, because that will help us get this x to a different level and find the area of that shape. So, in the last video, we learned that derivatives happen when you have a variable and an exponent denoted as the letter n. But to actually find it, you have to move that exponent in front of the variable like a coefficient. However, you have to have that exponent be leveled down by 1. An antiderivative is exactly the opposite. An antiderivative does not like what derivatives are doing. So basically, it's saying, instead of leveling it down a bit, we have to say that when you find the antiderivative, you have to have that x variable right there, but you have to have that exponent be leveled up by 1, and we have to divide that by your exponent plus 1. So technically, you're leveling up, not down. Okay, so this is a derivative, leveling it down a bit. And this is the antiderivative, because it means to level up the place. Now I think we understand the differences are. Let's plug it in. So we have the antiderivative is going to equal, we have x squared as our function, plus 1. That will become x cubed. But we have to divide that by our exponent plus 1. So 2 plus 1 is 3. So we have x to the third divided by 3. That is our antiderivative. Reversing the thing. Reversing the derivative. Now, we write that here and proceed to the next step. Now, here is when our integral comes in play. We have numbers 1 and 4, which is limiting the area between 1 and 4 on the x-axis. To help us calculate the area, we have to make 2 scenarios. So, scenario number 1, the lower number is going to be on the bottom. So we're going to put 1 right here. The upper part of the integral, or the bigger number, is going to be on the top, or the 1 on the top, or 4. Now, what we have to do is come up with 2 equations. We have to do 4 insert in for x for the 1, and for the second one, 1 into x for the other one. So we have 4 cubed, or 4 to the third, divided by 3. We have to subtract that because we're trying to find the area in here, and that is the difference between the two. 1 to the third power, divide that by 3. And we have our last step to work on. Now, all we gotta do is simplify, and we get the area and our answer to our shape. So we get to shape the shape. So 4 times 4 times 4, or 4 to the third, that is gonna be 64. Maybe after this video, I'll play Super Mario 64. Divide that by 3, but hang on. We have 1 to the third, so we have to do 1 times 1 times 1, or 1 divide that by 3. But we have to find a difference. simplify, and when you subtract the two fractions, you're gonna get 63 divided by 3. And when you do 63 divided by 3, and you got an answer, you got an even answer as 21 units squared. The thing is, we say units because we never really added like inches or feet or meters. But squared because it's a 2D shape on a graph. A graph with an X and Y is going to be a 2D thing. And not only that, 21 units squared is the exact area of this irregular figure right in front of us. We didn't have to use rulers, we didn't have to use tape measures, but we could use calculus. And that helped us calculate the area under a curve. I hope this video has helped you understand how to calculate the area under a curve. Thank you for watching Tao Penalize the Math Industry. Like and subscribe. And for the next video, we're gonna do another scenario, but instead of having an x squared, we're gonna add a coefficient of a different number. So 3x squared, because there's one thing that's a bit different. Like and subscribe!